This is the part B of vibrational spectroscopy. In this video, we will look for the anharmonic oscillator type vibration. In the last video, we have discussed about if the molecule vibrate like a simple harmonic oscillator. But actually, in real case, a real molecule act like an anharmonic oscillator. Let's see why. Because like that. For discussing about anharmonic oscillator, first we will say about what we have seen in simple harmonic oscillator. In simple harmonic oscillator, we have seen that when we plot potential energy versus internuclear distance R, where internuclear distance is the distance between the two nucleus or the two atoms of the molecule. At the equilibrium position, this distance is taken as R equilibrium, which is the bond length of the molecule. So what we have seen that when the distance increases, that means if A atom is here and B atom is here, this indicate the bond length or the distance of R equilibrium. This is the case of equilibrium position. When molecule is at the equilibrium position, their distance separating them is known as R equilibrium or simply their bond length. Okay, but when the molecule is stretched, that means when this AB molecule is stretched from this distance to this distance, we can see that the distance between both the atoms R has been increased from their R equilibrium value. So this is the R equilibrium position. From that it has been increased to some other R value. So this part indicate the molecule is in the stretched state, while this part indicate the molecule is in the compressed state, where in compression the distance between the two atoms is low. So let AB, for the molecule AB, let R equilibrium be the equilibrium bond length. At the time of stretching, the distance will increase to some other R value, and at the time of compression it will be decreased to some other R value. So simple harmonic oscillator curve indicate that when the distance between two atoms increases from this value to this value, as their R value increases, correspondingly their potential energy is increasing continuously. This what we can see in a simple harmonic oscillator. But if the molecule is real, for a real molecule we know that as long as the bond length increases from value, as the increase in bond length continues, there must be some point at which the molecule will break and it forms the atoms A and B. That means if we continuously increase the bond length between two atoms, there must be some point at which the bond will break, and this concept is discussed in an anharmonic oscillator. So if our molecule is undergoing anharmonic type of oscillation, which means that there must be some point of breakdown of the molecule. So it can be seen like this. And this constant value of energy indicate the point of dissociation or the breakdown point. At this point, there is no more molecule, there will be atoms only A and B. And this energy required for this value of energy required for the breaking down of molecule is known as its dissociation energy, DO. And this curve is known as Morse potential. This plot is generally known as Morse potential. So the plot of anharmonic oscillator is known as Morse potential, as the scientist chem Morse proposed this idea. Okay. Now we have to find the value for the dissociation energy DO. So for an anharmonic oscillator type molecule, when we plot potential energy versus internuclear distance, we can see there is some point where the energy is constant. That point is known as their dissociation point or breaking down point, at which the molecule is breaking down. That means its bond length is increasing and increasing. Here it is at the equilibrium position, and here the bond length is increased and as long as we go upward, the bond length is increasing, and thus there must be some point at which the molecule break down into the atoms A and B. Now we have to find the dissociation energy DO. Before that, there we have to study the other factor, which is known as the depth of Morse potential, represented by D. So here we have to study two factors. One is the depth of Morse potential, as we can see the distance between this x-axis and the dissociation point. So this is D, and which is known as the depth of Morse potential. Now we have to study the dissociation energy, that means the energy required to break that molecule. So the equation for depth is depth D is equal to mu bar by 4xc, where xc is known as anharmonicity constant. Its value is taken as 0.05. Now the dissociation energy is considered as, if the molecule is like this, there must be some ground state V equal to 0 here. So for dissociation energy, first we consider the molecules to staying at this ground state. So firstly, molecule is at the ground state, and at the time of breakdown, molecule is here, or the atoms are here. So the energy required for dissociation will be the distance between this final state and this initial state, that is this distance. So what's the difference between this DE and this dissociation energy DO? So DE is bigger and DO is smaller, and the difference is this much distance. And we know that for a vibrational energy V equal to 0, this value is known as their ground state energy. So dissociation energy DO can be written as DE minus ground state energy of that molecule. That means the energy at V equal to 0 level. To find the ground state energy, we should know the equation for the energy levels for an anharmonic oscillator. For simple harmonic oscillator, for a vibrational level V, we know that the energy is V plus half mu bar. Then the unit will be in centimeter inverse. If it is mu bar, the unit will be centimeter inverse. If it is h nu instead of mu bar, it will be joules. So this is the case of simple harmonic oscillator. Now we have to find the energy levels of our anharmonic oscillator. And by some derivations using quantum mechanics and Schrodinger equation, it has been found that the energy for any vibrational levels of anharmonic oscillator is given as V plus half into mu bar minus V plus half the whole square mu bar xc, where xc is known as the anharmonicity constant 0.01. So this is the equation for the energy of any level V. So before going to the selection rules of anharmonic oscillator, for simple harmonic oscillator, we know the selection rule is delta V equal to plus or minus 1. That is, the separation between the two levels should be 1 unit. For anharmonic oscillator, we have to find what type of selection rule is coming. Before that, we are just looking for the delta E values for a transition. For a general 0 to 1 transition, let's check what will be the energy required for simply. So for an anharmonic oscillator, if a transition occur from V equal to 0 to V equal to 1, what will be the energy needed? So how to find that for a transition from 0 to 1, V equal to 0 to 1, how to find it easily? It will be the energy of first level minus energy of 0th level. That is energy of final minus energy of initial. This is a general method. Final level is 1. So V equal to 1, we have to put the V equal to 1 value here, then only we can find E1. So first we can find E1. For that, in this equation we put V is equal to 1. So 1 plus half 3 by 2 mu bar minus 3 by 2 the whole square, that is 9 by 4 mu bar xc we will get. Like that we can find E0. For finding E0, just put 0 instead of V. And then we get half mu bar minus 1 by 4 mu bar Xc. Now we find E1 minus E0 for delta E 0 to 1 transition. That is this value minus this value. So 3 by 2 mu bar minus half mu bar will be equal to 1 mu bar, and minus 9 by 4 minus of minus, it will become plus. So minus 9 by 4 plus 1 by 4 it will come, which indicate minus 8 by 4. That is minus 2 mu bar Xc will come. So if we take mu bar outside commonly, we will get 1 minus 2 Xc. So this is the energy required for the V equal to 0 to V equal to 1 for an anharmonic oscillator. So if it was a simple harmonic oscillator, for V equal to 0 to 1 transition, we could find that it's h nu only, or we can say mu bar. Comparing these two values, we can find that for simple harmonic oscillator, we need mu bar energy for V equal to 0 to V equal to 1 transition. But in the case of anharmonic oscillator, we need mu bar minus some value. So it should be less than this mu bar. That is, if V equal to 0 is here, V equal to 1 will be here only, because the energy gap between this is less than mu bar, because mu bar minus some value it is coming. So it should be less than this original mu bar, which means that the levels of a simple harmonic oscillator, when we compare the levels of simple harmonic oscillator and an anharmonic oscillator, for anharmonic oscillator the levels are much closer compared to simple harmonic oscillator. Thus we can say that for a simple harmonic oscillator, if V equal to 0 is here, V equal to 1 will be here, and V equal to 2 will be here. But for an anharmonic Morse potential curve, if V equal to 0 is here, V equal to 1 will be here only, V equal to 2 will be here only. That means for anharmonic oscillator, the energy levels are much closer compared to simple harmonic oscillator. So consequently, the result is that the transition with 1 unit difference and 2 unit difference and 3 unit difference will be possible in anharmonic oscillator compared to SHO. So for a SHO, the allowed transition are with delta V is equal to plus or minus 1. For anharmonic oscillator, the allowed transition can be either with 1 unit difference or with 2 unit difference or with 3 unit difference, because the levels are closer. So the transition will be easier if it face a 3 unit difference. It will be easier because the levels are closer. So the selection rule for anharmonic oscillator comes like this. So let's say that if our molecule is like acting like anharmonic oscillator, from a 0th level it has many allowed transition. From 0 to 1 it can go, and 0 to 2 it can go, and 0 to 3 is possible. These 3 transitions are possible for vibrational spectra. But when we compare to the other higher levels, that is 1, 2, 3, we may expect that just like from V equal to 0 transition, from V equal to 1 we can expect a transition of 1 equal to 1 from 1 to 2, from 1 to 3, and from 1 to 4. But the problem is this type of transition is not seen in anharmonic oscillator. Only from V equal to 0 is most commonly seen. Most seen transitions are only from V equal to 0. Let's see why it's like that. So what we are trying to say is that from V equal to 0 to transitions are much easier or much common compared to V equal to from V equal to 1 transition. Let's see why like that. When we see the population of molecules in ground state and the first excited state, the population of molecule in the ground state will be higher compared to V equal to 1 state. When we say it using a Boltzmann distribution law, we can find the number of molecules in the first state and number of molecules in the ground state. We are comparing using the equation e raised to minus delta E by kBT. So this delta E can be replaced by Hc by lambda into kBT. So H will be Planck's constant 6.626 into 10 raised to minus 34 joule second into C velocity of light 3 into 10 raised to 8 meter per second. For lambda, for vibrational spectroscopy we are using IR radiation, for which lambda is generally few 10 raised to minus 3 centimeter it will come. There will be some magnitude before this 10 raised to minus 3, but commonly it's a range of 10 raised to minus 3 centimeter. So when we convert into meter, we will get 10 raised to 5 minus 5 meter. Why we using meter here? Because 1 joule we know it is 1 kilogram meter square per second square. So if we write a joule, it indicates there is meter. So whenever joule comes in that positions, in that section we should use meter, because 1 joule is kilogram meter square per second square. Kilogram meter per second square. Why it come? Because we know F is equal to ma, force is equal to mass into acceleration. For m, kilogram is the unit, acceleration meter per second square is the unit, from like this. Then this whole value is shortly known as joules. Okay. So we should put our 10 raised to minus 5 meters. Kb means Boltzmann constant. Its value is 1.38 into 10 raised to minus 23. And temperature, we are commonly taking a general temperature of 300 Kelvin, which is nearly a room temperature. So while doing this calculation, after doing we will get it is as 0.08. That means nearly 0.01. That means 1 by 100. That is the ratio between the molecules present in the first excited state and ground excited state will be 1 by 100, which means that in V equal to 0 level, if there is 100 molecules, if in V equal to 1 level, there will be only 1 molecule. So as there is the number of molecules are very less, there are transition from V equal to 1 is also less. So only the transitions from V equal to 0 is most commonly seen. This is because the difference in the high difference in their population. As ground state is more populated than excited state, the transitions are from ground state generally seen. In shortly, when we talk about anharmonic type oscillation, we generally talk about 0 to 1 transitions only. 0 to 1, 2, 3 transitions only from 0 is considered. Now we have to look for the fundamental vibration in anharmonic oscillator, fundamental vibration, and what is the first overtone indicating, second overtone, and hot bands. These are the other topics from anharmonic oscillator. So first topic, fundamental vibration. What does it mean? Fundamental vibration means the vibration from ground state to first excited state, that is 0 to 1. So as we have already found in this part, the 0 to 1 transition needs an energy of mu bar into 1 minus 2xc. The derivation we have already discussed. So the energy required for 0 to 1 transition for an anharmonic oscillator is mu bar into 1 minus 2xc. Okay, where mu bar is the wave number of the radiation we using. Next we have to study first overtone. First overtone means the other transition, the next possible transition. Just like we are saying first runner-up. First runner-up means second position. Like that, first overtone means from 0 to second level. 0 to second level transition is known as first overtone. So the energy required for first overtone transition is delta E V equal to 0 to 2. So E energy of final state minus energy of initial state. Final state is 2. So we have to find E2 minus E0. E2, how we should find? We should use the equation V plus half mu bar minus V plus half the whole square mu bar xc. Instead of mu bar we can use h nu also. That is also correct. So we in the place of V we will put 2 plus half. That is 5 by 2 mu bar minus 5 by 2 the square, that is 25 by 4 mu bar xc. This is E2. E0, as we can see from last derivation, half mu bar minus 1 by 4 mu bar xc. Now we have to subtract this value from this value. E2 minus E0, we will get 5 by 2 mu bar minus half mu bar, 4 by 2 mu bar, that is 2 mu bar, minus 25 by 4, minus of minus will plus 1 by 4, that is 24 by 4, 26 by 4, sorry, 24 by 4 minus 24 by 4 will be 6, that is 6 mu bar xc we will get. So when we take this 2 mu bar as a common factor, we will get 1 minus 3 mu bar xc. This is the energy of first overtone. First overtone means 0 to second level will be the transition. Now we go to second overtone. Second overtone means the transition is from 0 to 3. So the delta E from V equal to 0 to 3 will be equal to E3 minus E0. So we have to find E3, 3 plus half mu bar will be equal to 7 by 2 mu bar minus 7 by 2 the square, then 49 by 4 mu bar xc. E0, as we can see, half mu bar minus 1 by 4 mu bar xc. Now we have to subtract this value. E3 minus E0 will be equal to 7 by 2 minus half 6 by 2, that is 3 mu bar, minus 49 by 4 plus 1 by 4, 48 by 4, that will be 12. So it will come 12 mu bar xc. Now we take 3 mu bar outside, we will get 1 minus 4 mu bar xc. So this is the second overtone transition, the energy required. Now we go for hot bands. What does hot bands mean? So hot bands, from its name we can find that there is some relation with heat. Hot, the word hot indicates some high temperature or some heated thing they are intended for. So that means hot bands are the bands which are weak at low temperature, weak in intensity at low temperature, and strong in intensity at higher temperature. So when temperature of the molecule or temperature of the substance is low, it will give a weak peak. That means less intense peak. When the temperature of molecule is increased, it will give the same peak will become more intense. So for a low temperature case, if the peak is very less intense, for high temperature its intensity will be high, like that. So such transition is from V equal to 1 to 2. As we have already said, V equal to 1 level is less populated. So that means if 100 molecule is present in V equal to 0 level, in V equal to first level there will be only 1 molecule. So the transition from these levels are very less in number. In spectroscopy, the very important thing is intensity is depending upon how much transitions occur in that level, within that levels. So intensity is always proportional to number of transition. This concept is very important for in future discussions also. So intensity depends upon number of transition. As here there are many molecules, number of transitions from this level will be high and it will give highly intense peak. But from 1 to 2, as there are number of molecules very less, the number of transition will be less, this intensity will be very low. But once we increase the temperature of the system or temperature of the substance, what will happen? Some of the molecules present in this ground state will jump to first excited state. Now the first excited state will be more populated than the earlier case. So the number of transition from this level might have increased. So as temperature increased, number of transition will, population of the level increases first. Population of first level increases. As population increases, number of transition from that level increases. As number of transition increases, intensity of the corresponding peak will be intense. So such type of transition are known as hot bands. The peaks obtained due to such transition is known as hot bands. Hot bands are the bands or the peaks which will be less intense at low temperature, and when the temperature is increased, the peaks intensity will be increased. So generally it is from 1 to 2 transition they are meant for. Now we have to find the energy required for a hot band. That means hot band means the transition is from 1 to 2. So E2 minus E1. So for E2, as we have seen in last derivation, it is 5 by 2 mu bar minus 25 mu 5 by 2 mu bar minus 25 by 4 mu bar xc. At E1, this is E2 and the E1 is 3 by 2 mu bar minus 9 by 4 mu bar xc. Now we have to subtract this value E2 minus E1. We will get mu bar minus 25 by 4 plus 9 by 4. That is minus 16 by 4. That is minus 4. Minus 4 mu bar xc. Taking mu bar outside, we will get 1 minus 4 mu bar xc. So when we conclude the energy needed for fundamental vibration, first overtone, second overtone, hot bands, we can easily say, just like we have by hearted everything. Fundamental will be 1 mu bar, then 1 minus 2 xc. Then first overtone will start from 2 mu bar, then 1 minus 3 xc. So correspondingly second overtone we can easily write as we follow this pattern 1 2, then it will be 3 mu bar. This 1 is constant, 2 3, then it will be 4 xc. Hot band is little different. It's just similar to this fundamental, that is 1 mu bar and 1 minus. Up to this it is similar. Instead of 2 xc it will come 4 xc. Like that we can easily study the values, energy required for this type of special transitions, where xc is the anharmonicity constant, mu bar is the wave number. Mu bar is the wave number, that is 1 by lambda. It will be in centimeter inverse. Now let's compare the things we have studied in the case of simple harmonic oscillator and anharmonic oscillator. The first difference is their plot. In simple harmonic oscillator, it is a regular inverted parabola we are obtaining in that position. For anharmonic oscillator, the plot we obtained is known as Morse potential. So this is the major difference. And the second one is in their selection rule. Here delta V plus or minus 1 is only possible. Here delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. are possible, etc. There can be anything, not only up to 3, plus or minus 4, like that is also possible. And the other point is the energy values EV is equal to V plus half mu bar only. Here EV is equal to V plus half mu bar minus V plus half the whole square mu bar x is coming. For this delta E for any transition, any V equal to V plus 1 transition, the value of energy required is h nu, or we can say mu bar. But here we are not studying it like by hearting. We have to find from E final minus E initial. No need of by hearting all the values. Just keep this in mind, and using derivation we can easily find the answer. So these are the important points.